My name is Evgeniya Sukhodolskaya, or Jenny, and today we're going to talk about vector databases as an instrument of big data analysis. And you know what? I'm happy that I'm giving this talk today because I glanced in the schedule and I saw before and after me a lot of stuff about RAG. And I think this is exactly the conception that everybody thinks that vector search is all about RAG. Well, vector databases can be used as a knowledge base in RAG, indeed, and I would say it's still a very good choice and a very popular choice, even though the RAG is trying to be killed and resurrected on socials basically every week. And no, it's not that. There is an evolution to it, and now it's Agentic RAG or even MCP-based RAG solutions. We also invest in our MCP. Yet to vector search, there is a little bit more than just RAG and being a knowledge base. And there is a room to it. And it's exactly the reason why vector search solution and full text search solutions are not gonna merge in one, even though in the late years, they are trying to converge a lot. And this room is exactly what I wanna study today and explore with you to see how vector search can be used as something more than just a knowledge base, so as an instrument of a data analysis. So today we're going to look at the three components: visual data analysis, which is obviously not at scale, then vector search for scalable data analysis, and then how you can turn it into a business solution. And it's a little bit more of an overview talk. My goal is honestly just to inspire you a little bit, because I feel like this part of the vector search is not so well known. Let's start. But before we start, I want to give you a little bit of motivation why I'm talking about this today, so you don't leave with a feeling that vector search dedicated solutions are trying to invent something just to not die with that RAG today. So you should be interested in today's talk in the situations when you, for example, have a lot of data and you don't know what to do with it. We all have a lot of unstructured data today. For example, it's documents, code base, media, videos, whatever there is. And this data grows every day by billions. And trust me, there are like a lot of applications where you need to study it and analyze it, and you don't know where to start. Or you know where to start, but the solutions of this data analysis are extremely heavy or costly. For example, you can't ask your LLM to analyze 1 billion points, or you can, but you're extremely filthy rich. And what's worse, you finally found all the automated solutions for your data, it's in production, but then everything starts drifting and shifting, and you need to start all over again. Source, well, just trust me, I worked in the advertisement moderation when 1 billion of points comes every day and you don't know what to do with it because everything is changing every second. And here I want to propose you actually a non-standard solution, vector search solutions, dedicated solutions for data analysis. Why them? Well, the most basic thing that I wanted to say is that vector search solutions are dedicated to store billions of data points. And not only they are dedicated to store them, but they are based, sorry for tautology, on a base principle. So they are working more as a search engines. So they not only store billions of vectors, but they are also designed to retrieve them faster. What does this retrieving bring to the table when it comes to data analysis? So which basics do we need to know? Beyond that, the vector databases or vector search engines are good for working with vectors at scale. Well, let's look at the vector search. I think all of you know that vector search is about working with vectors. Usually you get vectors out of dense embedding models, even though it's not a limit, but here I'm gonna explain and explore mostly solutions around them. And these dense encoders are convert whatever data modality you have into a vector, which is placed into a vector space. And the points, which are more semantically similar, so similar in a way you can describe, are placed more closely in this semantic space. What do I mean by more closely? You can measure this numerical closeness by different metrics, but mostly it's cosine similarity, because most of these dense embedding models are actually trained to use this metric to put the more similar semantically data points closer. This metric spans from -1 to 1, where the perfect match is 1, and the absolutely dissimilar points, so opposed to each other, have the cosine similarity of -1. And this feature actually allows for the specific ability of vector databases to do not only similarity search, but also dissimilarity search. So cosine similarity of a vector with its opposite is always -1. So if we multiply a data point vector by -1, we get the complete opposite. So with any vector search solution, if we find something completely similar to our opposite, we get a dissimilar point, the most dissimilar point we have, to our initial point. And that's how we come to dissimilarity search. Dissimilarity search and similarity search combined, that's already a big arsenal of instruments for our data analysis. And it can be done in any vector search solution. In dedicated solutions, you can also add specific features which are designed and possible due to their interfaces. For example, in Qdrant, we have certain interfaces allowing us to operate with vector math because we just want to fill this room of vector search beyond simple semantic similarity or dissimilarity. So we, for example, are able to provide distance matrices between points, which you can see here on the screen, or we also have a query points API, which allows us to do different operations with similar and dissimilar data points and the closeness to them, and move and study our points in the vector space. For example, do recommendations or discovery. And that's what we are going to use exactly for data analysis, which I am finally switching to. So let's do the first simple step. Say you have data in front of you and you want to analyze it. It's unstructured and you want to derive some specific business case out of it. And the first thing that you would logically do, you would prefer to look at it because we understand a lot just seeing something. Well, let's, for example, take a Midjourney dataset, the dataset of images, and say you're coming with it to a dedicated vector solution, for example, 2 hours. And you are opening our web UI, which is designed specifically for studying your data visually. Let's see, how can we study this images dataset? Firstly, let's start with one point and try to look at its neighbors. Maybe follow some semantic similarity paths. What are the styles of the image that match each other, and how can we derive some certain patterns from it? That already gives us some idea what do we have in our data, but probably we want to see a little bit of more data. So you want to see more points depicted at the same time, and you can do it with a force-directed layout graphs, which attract similar points together and push away the dissimilar points. It's very nice to look at it, but it already looks a little bit too crowded. So here you stop understanding the relationships between data points. Then you can look at the minimal or maximal spanning tree of this graph and depict your data with its strongest similarity relationships and already see some clusters in your images and data points. For now, we just used simple similarity and dissimilarity. But what if we want to see even more? We want to see all of our points at the same time visualized, so we maybe can spot some clusters. And we can do that on our dashboard too. And here you can see the sample of 500 points from Midjourney dataset being depicted. But my goal is not today to show off my dashboard, even though it's a little bit of a goal, but not the final one. My goal is to explain how it's possible with dedicated vector solutions. And the last one, for example, is possible due to dimensionality reduction. Why dimensionality reduction is so good with dedicated vector search solutions? Well, there are several dimensionality reduction algorithms which are pretty popular and known and are there in the data science libraries. For example, UMAP or TSNE. Here you can see a UMAP representation of our Midjourney dataset. And all of them take a lot of time and rely on building a distance matrix of initial high-dimensional data. They need that to compare these distances with the 2D representations they build, so they are accurately projected. Well, because we can't understand high-dimensional embeddings relations, I can't think in 5D. So this distance matrix is one of the toughest steps for these algorithms. And vector search solutions with specific interfaces like ours can provide this distance matrix, and the rest is much faster to compute. And this is not the only type of data visualization and analysis algorithms which use distance matrix. Another one is clustering. Clustering is actually very important for studying your data because, well, you want to know what's there, maybe devise some hierarchy, maybe find some taxonomy that you're going to use, some categorization. And for that, you will definitely need some clustering to be done. And all of those famous clustering algorithms, for example, in the simplest k-means, can be used much faster if you provide them a distance matrix between the sampled points. Where do you get it? From a dedicated vector search solution. So we already have some visualization of our data, and we know how to study it visually with our vector search solutions. And maybe we have already some intuitive ideas of how to operate with it. But this is not a scale, because at scale, well, we can't analyze billion points with our eyes. And here I'm coming to the part, which is actually was the name of this talk, vector search for scalable data analysis. So at scale, we can't analyze our data visually, and we want to analyze it algorithmically. So get some automated answers about it. And let's think which questions would be asked to our data when it's all full in front of us and structured, and we want to get some automatic answers. Well, the first one would be, how various is my data? For example, you have a lot of data points. You want to see either within a category or a class, or maybe within the whole general billion point data set. What are the possibilities? What are the edge cases? What is the variety of your data points? And you could actually sample it, but the random sampling that you could do has a risk that you're going to get all the similar points from the one part of the vector space. This is not very interesting. So here comes DISsimilarity-based sampling, which is possible with dedicated vector search solutions. And it uses DISsimilarity search. The idea is pretty intuitive, and that's how it looks. So you get a point and you iteratively sample the points which are the most dissimilar to already selected points. This you can do in dedicated vector solutions at scale. For example, in Qdrant, you can do it using our recommendations API plus best score strategy and provide all the new samples as negative examples. The specific solutions allow to do it at scale because they search fastly through billions of data points on a built vector index and find the dissimilar points. Another question that you can ask yourself after you devised all the classes and clusters is about anomalies. Are there anomalies in my data? And once again, with vector search solutions, which can be used as a zero-shot instrument for data analysis, and that's why it's so interesting, this is pretty intuitive how to try to use it. So here you can see that the anomaly is something that doesn't fall within a cluster of data points. So it's somewhere far. And how can we turn this intuitive 2D image in something more applicable in high dimensions and billion points? Well, as a simple solution, we can follow this algorithm. We can identify the representative of a class, of a cluster, or a cluster. It can be midoid or centroid. And then here you can use a distance matrix API to find it. It can be a category or a class name, which is actually possible to use not only with textual data, but also with multimodal data. For example, I will show later examples of e-commerce, where you can describe a category and it's going to be a cluster representative, and the images in the e-commerce are going to be cluster members. And it can be just an ideal candidate description, so the perfect representative of your class. And then you can either find the furthest point from your cluster center of the same class, for example, and then it's going to be an anomaly, or you can find the borders of this cluster, so some space, in which all cluster representatives, so all points belonging to the cluster and fitting its description, are basically gathered within, and you want to find a border. So this border can be simply, for example, found with finding the x, where x is metaparameter furthest point from the cluster representative, and x furthest point where x is metaparameter from the cluster representative. And for that, you are going to use the DISsimilarity search, since we're searching something furthest. And then you can use the similarity score between them as the cluster border or a cluster threshold. Now everything is simple because all the points that fall outside of the threshold or outside the border are anomalous to this class. And you can scale this to many classes and use it in different solutions. For example, in e-commerce, you could use it as something as an outlier detection, where you can find anomalies within your category or some candidates which don't look like a specific representative of the class, which will allow you, for example, to create more granular categorization. Or even if you're working with labeled data for your training algorithms and you want to zero-shot study it with your vector solution, you can just detect mislabeled data being anomalous to its category. So we can study our data, and there are a couple of applications that I show how we can do it in a more statistical static way before we have any business solution. And I can motivate you even further, because this one can be turned into a solution when your data dynamically changes in production, shifts and drifts, and you don't know what to do with the new incoming points. So imagine, how can we use a vector search solution when you have a new incoming point to your billion points as an advertisement moderation or spam detection or anything like this? And how can you utilize vector search solution for this data analysis in production? Already looking at this picture, which I showed before, you can see the intuition behind some solutions which come to mind. For example, for a new incoming point, you can detect if it's an anomaly to your class or some of your classes that you already know in your stored data set. Or you can check if there are some duplicates, for example, some content duplicates or some media duplicates, which is happening a lot in production. Or you can even use classification right in production, judging by the nearest neighbors of the point and doing the majority voting, because some of the points you probably will have already labeled, and then you can just propagate your labels among all the new arising data points. And if they are gray zone, you can actually study them already with more sophisticated non-zero shot solutions. And what's interesting, that all of these three classes that I showed are actually the real use cases from our clients that used vector search solutions for that. And there are much more to it that you can think about how to apply vector search solutions in a zero-shot setup on the big scale, for example, for vertical farming, in food industry, for ecological monitoring, or you can do some deduplication in your code bases or documentations. All of that is attractive because it requires a zero setup, and you can try it out immediately with your different data sets, which is pretty beneficial considering how fast-pacing our current AI business world is. All in all, I'm super happy to discuss any additional ideas that we have and how can we use them in vector search solutions. And I'm a certified yapper, but I have only 30 minutes here. So please contact me and I'll be happy to connect and chat. Bye-bye, guys.